Hello everyone, I am an astrophysicist from Penn State University, and I'm here today to talk to you about DeepMoon, identifying lunar craters with artificial intelligence. So this is the basics of how our algorithm works. The input is a picture of the moon. Once we feed it to our algorithm, the output will be these rings, and so the rings correspond to the locations of the crater rims, and through this mechanism we can determine where the craters are. And so it's particularly a convolutional neural network, and we obtain training data from many human experts who painstakingly classified all these craters. And then we train and validate it on 60,000 images, which is about 2/3 of the moon, and then we test it on the remaining third. So these are the kind of predictions that we get. So the left panel are all the craters that our algorithm, that DeepMoon, discovered. Where on the right, those are all the craters that the humans classified. So the blue circles, those are all the craters that our algorithm discovered, that the humans also discovered. The red circles, those are new craters that our algorithm discovered that the humans did not discover. And then on the right panel, you can see a few purple circles which represent craters that the humans discovered that ours failed to recover. But in summary, you can see there's a lot of blue and red circles, which means that our algorithm is detecting the craters that humans classified as well as many, many new craters. So what are some of the applications? What are we going to do next with this? So the first is we can push to smaller craters. It turns out there's literally hundreds of thousands of craters currently undiscovered on the moon, not because they're hard to detect necessarily, but just because there's not enough manpower to physically count them all up. But with this algorithm of automating the process, we can now push to smaller craters and detect more of them. The second application is to classify craters on other bodies as well. It turns out that with the exception of the moon, Mars, and Mercury as well, there's very few bodies in the solar system that have been thoroughly and systematically studied. And so, for example, Vesta and Ceres in the asteroid belt, and Mimas and Tethys in the Saturn system, they have many craters on their surface, but there's been very little human effort to systematically analyze them. And the hope is that our long-term goal is that we will be able to apply our algorithm to all these bodies. And we've already demonstrated that it's possible to do this, at least in principle. So this is an image of Mercury, and so when we pass this image of Mercury through our algorithm, and remember, our algorithm was trained exclusively on the moon, it had never seen an image of Mercury in its life, and yet it's still able to recognize and classify where the craters are. It's maybe not getting every single crater, there's still further improvements that need to be made, but surely this demonstrates that at least in principle this is possible. In conclusion, I'd like to just show you a little bit about how craters can inform some big questions. In particular, how much total rocky material was present in the early solar system? It turns out that this is not a simple question, and it's very important to know the precise answer because the solar system is chaotic, which means that if you just change the initial conditions a little bit, you can arrive at very different answers. It's important to constrain this quantity. The second is, how did the amount of rocky material change with time? Was there a huge cataclysm of explosions just pounding the moon at one time, or was it more gradual and through time? And by analyzing and dating the craters, we can get a sense of this chronology of how the impacts hit us. And finally, was the material contained in the largest or smallest bodies? It turns out that the larger the body it is, the more likely there is to be a catastrophic impact. And in fact, the moon itself formed from a catastrophic impact between the early Earth and this hypothesized body Theia. It's called the giant impact hypothesis. And so by analyzing the size of the craters, we can get a better sense of how violent the history might have been. I hope that in this short talk I've given you an explanation of what our algorithm does and how craters are important. Thank you very much.